Hello everyone, welcome back. Now let's look at this practice problem. An experiment was planned to compare the mean recovery time in days from the common code for persons given a daily dose of vitamin C versus those who did not receive a supplement. Test whether there is a difference between no vitamin and vitamin C at alpha equals 0.05. So the information we have here is given in this table. So we can just write down what's the meaning for those information. So we have no vitamin, and then we say this is for this first population, population 1, and then the mean is mu1, and then this vitamin C group is population 2, we say mu2. So sample size, we have n1, n2. Sample mean x1 bar, x2 bar. And then we have the population standard deviation for the first one, sigma 1, and then sigma 2. Okay, that's all we know here, and then we can just again go through the 5 steps. So null hypothesis, always mu1 minus mu2 equals 0. So this is always. And then this sign is determined by the question. So there is a difference. So this difference tells us the claim does not equal to two-tailed. And then for critical value, then we have to put alpha level 0.05 given from the problem, and then the sign we have. So does not equal sign tells us this is two-tailed. So two-tailed means we have two critical values from both sides. So we're gonna just draw this normal curve here, and then 0 in the center. So the significance level alpha is actually the rejection region we put in this normal curve. So from two ends. Since this is symmetric, we have alpha equally distributed to two tails. Then each side we have alpha divided by 2. So in this case, alpha equals 0.05. So 0.05 divided by 2, that's 0.025. And then that's why to the right you have 2.5%. So this number is going to be a positive value. This number is going to be a negative value. And then to the right you have 2.5%. So that's C sub 0.025. And then this is going to be same as this value, but with different sign. So negative Z sub 0.025. So we're going to check this table out from the table. So actually we can use a T table. So Z sub 0.025, T curve and Z curve. So we mentioned that T curve with positive infinity degree of freedom equals to Z, right? It's same as the standard normal curve. So we can check T sub 0.025 with degree of freedom equals positive infinity. Then let's see what the value is. So we pull out the T table. T sub 0.025 with the degree of freedom equals positive infinity. Then we have 1.96. So that's 1.96, and this is negative 1.96. So the critical value is positive and negative 1.96. So from these two values, cutoff values, to either end, more extreme, lower or higher than the higher one, lower than the lower one, we call it then the value to extreme. Test statistics still the same as before. Put the formula there and then finish calculation, we got 2.07. This is a value combined with the evidence and the assumption of the null is true. Then we put 2.07 in the curve. So 2.07 is here. So that lies within the extreme rejection region. That means it is extreme. So we reject the null hypothesis H0. Reject H0. And then conclusion going to be there is enough evidence since we don't want the null hypothesis. We assume it's true, and then we got a number stating that it is true, but the number is too extreme to be true. Then we don't want the assumption. The assumption might be wrong, right? So we reject the assumption, reject the null hypothesis. If we reject the null is an either or choice because we have two conflicting hypotheses, then we prefer the alternative one, and then that is the claim. And then conclusion always in terms of the claim. There is enough evidence to conclude that the recovery time from the common cold for people who take vitamin C is on average significantly different than those who take no vitamin C at alpha equals 0.05. Don't forget to mention the significance level when you make a conclusion. So that's for using z-test, testing the difference between two means using z-test. And then we're going to look at the t-test scenario. So for t-test, that's when sigma 1, sigma 2 unknown. And then the assumption, then we actually want to use this t distribution. And to make sure the sampling distribution follows the t distribution, then we have the following assumptions: a random sample, independent, approximate normal, or more than 30 sample size. So that's the assumption. And then we further look at two cases here. So the first one is when although we don't know the population standard deviation, but we can assume the relationship between the two population standard deviation. We assume they're not equal. That's one case. We assume they're approximately equal each other. That's another case. So based on different case, the degree of freedom of the t distribution varies. So if we assume they're not equal, then the degree of freedom is the smaller of n1, or the smaller of the degree of freedom from each individual sample. So let's say we have n1 equals 9, n2 equals 4. Then n1 minus 1, that's 8. n2 minus 1, that's 3. So we're going to say the degree of freedom equals 3 because we want the smaller one of these two numbers. 3 is smaller than df equals 3. And that's for assume population standard deviation unequal. And then the test statistic is similar to before, just change this the population variance to sample variance, and then the procedures remain the same. When we assume equal variance, then we have to force the sample variance to be similar. Then how to still use the same but remain the information. Then we have this pooled variance here. Pooled variance. It's actually the weighted average for the two sample variances. The weighted average. So the weight is the degree of freedom. So weight times the first variance, and then plus the weight times the second variance divided by the total of the weight. So that's a weighted average of this two. And then we call that pooled variance. Then SP is square root of SP squared. Then we call it pooled standard deviation. So that makes sense because we already assumed the population standard deviation, they're the same. So for the sample one, should be using the same one. And then if we don't have the same one, then we'll pull those together. And for the denominator, it looks like a little difference, but that's actually still the same as before. So this is same as square root of sp squared over n1 plus sp squared over n2. Because you can pull sp squared out and then times 1 over n1 plus 1 over n2, because that's a common term, and take square root. And then square root of sp squared, that's sp, times square root of 1 over n1 plus 1 over n2. You might say sp could be negative, but that's from mathematical calculation. Actually, sp is a standard deviation, always more than 0. So we can just say it's sp. Then for the degree of freedom, we use the pooled variance total weight. So that's the degree of freedom of the t distribution. So from here, n1 plus n2 minus 2. So two different cases, but the procedure still remains the same. We just need to be careful to look at the question and then which case it is. Now we have a couple of examples and practice problems. Now let's work on those. Example 1, to see if review session helps that 1369 students study for the exam. I take a pool of 9 students who went to a review session and found they had an average. So then we have 2 populations. We can write it down. The information review, yes, that's a population, and then population mean we say mu1, and then we have review, no, that's population mu2. And then from this population, we collect sample. So the sample size n1 is 9, and then average test score 78.2. So x1 bar equals 78.2, and standard deviation, that's sample, not population. So S1 equals 4.1. 12 students from did not attend review session part. So we have 12, x2 bar equals 65.3, and then S2 equals 4.9. We assume n equal population variance. So sigma 1 does not equal to sigma 2. That tells us the degree of freedom equal of the t distribution equals smaller of n1 minus 1 or n2 minus 1. So n1 is 9 minus 1 give us 8. And then n2 is 12 minus 1 give us 11. So 8 will be the degree of freedom. So df equals 8. That's from the assumed unequal population variance. Then we can start our 5 steps. So step 1, state the null and alternative hypothesis. So the null hypothesis is always mu1 minus mu2 equals 0. The alternative hypothesis is always mu1 minus mu2. And then what 0? Yet to be defined. Let's look at the question. Is there enough evidence to suggest there is a difference? When you ask whether there's a difference, so positive difference, negative difference, right? All okay, and that's two sides. So equal and does not equal. That's step 1. State the hypothesis, and then step 2, we want to look at the critical value. So put alpha here. So alpha will be, there's no given information, so by default we use 0.05. So alpha equals 0.05, and then the sign that tells us two-tailed, and then sigma 1 does not equal to sigma 2. That tells us df equals 8. So then we can draw a curve, represent the t distribution. So 0, two-tailed means the rejection region we have from two sides. And then alpha is actually the whole rejection region, 0.05. So because of symmetry, each side you got alpha over 2. 0.05 divided by 2, that's 0.025. And then this is 0.025. So this number is going to be t sub 0.025 with df equals 8. So this is just the negative part. So negative 0.025 degree of freedom 8. So we can check the t table to get this value. So 0.025 is right here, degree of freedom 8, 2.306. So this equals 2.306, and then we have a negative 1. And again, if you have two-tailed, two-sided test, then you have two critical values. That's plus, or that's my positive and negative 2.306. The step 2. And then step 3, we have the test statistic. So t equals x1 bar minus x2 bar over square root of s1 squared over n1 plus s2 squared over n2. So that's actually 78.2 minus 65.3 divided by, just plug in, square root of 4.1 squared over n1, which is 9, plus s2 squared, 4.9 squared over 12, that's n2. So calculate that out, we got, let's pull the calculator out. Okay, now we got the calculator ready. Type it in. 78.2 minus 65.3 divided by square root. That's power of so square root of 4.1 squared divided by 9 plus 4.9 squared divided by 6.56. So we can write it down. That's the test statistic. And then step 4, we're going to make a decision. We can draw a line representing this 6.56. So this is a value of 2.3, right? So 6.56 is right here. So it is in the rejection region, and then it is very extreme actually. So too extreme to be true, then we reject the null, right? So we can say test statistic equals 6.56 is even more than the positive cutoff value, or we call it critical value, 2.306. So we reject the null hypothesis. That's step 4, reject the null hypothesis. And then we have a step 5. Conclusion. There is, since we reject the null, right, there is enough evidence to conclude the claim. What is the claim? Conclude that there is a difference in average test score. at alpha equals 0.05. So never forget to state your significance level, because this might affect your decision in step 4. So this is also important. And then that complete this example 1. So example 2, still same setup, but now we assume equal population variance. Now let's see the difference. So we'll just make a correction on top of these previous answers. So the information we have still remain the same, but we have sigma 1 almost equals sigma 2. So that tells us we need to calculate the pooled variance, so which is n1 minus 1 as 1 squared plus n2 minus 1 as 2 squared over n1 plus n2 minus 2. Because the population information are already same, so for the sample one we try to use the same value, so we call it the pooled variance. And then so go back to the example, we have n1 equals 9, so that's 9 minus 1 as 1 squared, which is 4.1 squared, plus 12 minus 1, 4.9 squared. 12 minus 1, 4.9 squared, over 9 plus 12 minus 2. So that tells us what? Let's see, what's the pooled variance? So we have 8 times 4.1 squared plus 11 times 4.9 squared. Eight times 4.1 squared plus 11 times 4.9 squared, and then divided by 9 plus 12, n1 plus n2 minus 2. Then what we have? We have 20.98. Then the pooled standard deviation is going to be square root of 20.98, which is, let's see what it is, 20.98 to the power of half the square root, 4.58. And degree of freedom equals n1 plus n2 minus 2. So that's 9 plus 12 minus 2. That's 19. So that's the degree of freedom, and then that's the pooled standard deviation. So now we can start the 5 steps. Since still the same question, so this null and alternative hypothesis won't change. And critical value, let's see. So critical value will change. So we just erase that. So alpha equals 0.05 does not equal sign, and then that gives us two-tailed. So mu1 almost the same as sigma 1 almost the same as sigma 2. That tells us degree of freedom equals 19. Then we have t critical value equals t sub 0.025 with degree of freedom 19. So we're going to check 19 here. So 2.093, 2.093. So we write that down. So this is negative 2.093. Then critical value is going to be positive and negative 2.093. And step 3, test statistics. So the formula changed a little bit because we're using the same pole variance. So we can rewrite it as SP times square root of 1 over n1 plus 1 over n2. And then the numerator won't change, but the denominator changed. So SP 4.58, right? So we plug in 4.58 and times square root of 1 over n1, which is 9, and then n2, which is 12. So then the test statistic will be 8.2 minus 65.3 divided by divided by what? 4.58 times square root of 1 over 9 plus 1 over 12. So we take square root product with that, that's the denominator. And the answer is going to be 6.39. 6.39. So step 4 will be test statistic equals 6.39, which is more than 2.093, more extreme than that. And that value is actually here. So very extreme. And then so we reject the null hypothesis H0. And step 5, there is enough evidence to conclude that there is a difference in average test scores at alpha equals 0.05. So that completes this example 2 when we assume equal population variance. As you can see, no matter which way we go, the overall result still remain the same. But for question, for practice problems, these will always be given to kind of lead you to the formula that you need to use. And then the practice problem, the last question for this chapter, and actually last slide for the whole semester. Let's look at this one. To test the effectiveness of an anti-plaque rains on plaque buildup, 7 people each were selected for a control group, no rains, and an experimental group that received an anti-plaque rains. So again, same thing. We state population 1. So just write down all the information we have. That helps us to kind of understand this question better. So population 1, population 2. So we have mu1, we have mu2 here. So population 1, we can say that's the rains group, and then population 2, control, no rains. And then we have the mean, mu1, mu2, and then let's see, the control group had an average of 1.26. So this is control group, right? So we have x bar equals 1.26 plaque index with a standard deviation of 0.32. The experimental group had an average of, so x1 bar equals 0.78, and with the standard deviation as 1 equals 0.28. And then we know alpha equals 0.1. So we don't know. So sigma 1, sigma 2 unknown, because we don't know the population information. So population standard deviation unknown. And then the relationship is actually didn't state in this question. So by default, we use sigma 1 is not equal to sigma 2. In a real practice problem, this will be given. So sigma 1 does not equal to sigma 2. And then let's set up the 5 steps. Step 1, null hypothesis, mu1 minus mu2 equals 0 like always. H1, alternative hypothesis, mu1 minus mu2, what? 0. So this time we need to look at the question, read the question carefully. So is Rayans perform better? Rayans perform better means Rayans has less the plaque index, because the numbers we have representing the plaque index. So actually we want Rayans group has less plaque index. So based on the claim, right? Better means less plaque index. So Rayans group is mu1. So that means mu1 smaller than mu2. So that's why we got this smaller than here. So let's use a different color. Smaller than. So it's not always when you see the term better, you have a more than sign. So we have to determine this sign based on the setup and what the question is, the meaning of those numbers, values. And then we can do step 2. Step 2 means critical value. We need to look at alpha equals what? 0.1, given from the question. Alpha equals 0.1. And what sign we have? So this is one-tailed. One-tailed, left-tailed. And then we assume sigma 1 does not equal to sigma 2. So df equals smaller of n1 minus 1 or n2 minus 1. So n1, n2, we haven't stated here because they both equal 7, right? 7 people each. So n1 equals 7, n2 equals 7. So it doesn't really matter. df equals 7 minus 1, 7 minus 1, the smaller of 6. That's 6. And then we can draw this normal, this t-curve. So 0 in the center, smaller than one-tailed left. So we draw this little area from the left. So that's alpha equals 0.1. And this is a negative number because less left of 0, smaller than. So this value is going to be negative t sub alpha, which is negative t sub 0.1 with df equals 6. We check this value from the table. So t sub 0.1 degree of freedom equals 6. T sub 0.1 degree of freedom equals 6. 1.44. That's a reading. 1.44. So we write down this is negative 1.44. So always don't forget the sign we put in front. It's a negative number because it's left of 0. And then the critical value, negative 1.44. Then we can have step 3. Step 3 will be the test statistics. So x1 bar minus x2 bar over square root of s1 squared over n1 plus s2 squared over n2. So plug in x bar 0.78 minus x2 bar 1.26 divided by square root of 0.28 squared over 7 plus 0.32 squared over 7. So we're going to calculate this out using the calculator we have here. So 0.78 minus 1.26 divided by square root. So that's power of half. 0.28 squared divided by 7 plus 0.32 squared divided by 7. And then let's see what it is. Negative 2.99. Negative 2.99. And then step 4, we can make a decision. So we're going to again draw the curve. So 0, and then this value is negative 1.44. So negative 2.99 lies here. So that is actually test statistic equals negative 2.99. It's even smaller than the already extreme value, the cutoff point 1.44. So it lies in the rejection region. So this is the rejection region. Reject. No hypothesis. So if we reject, then step 5, we can make a conclusion. There is enough evidence to conclude the claim. And what is the claim? To conclude RANS perform better at alpha equal 0.1. Okay, that's the step 5. So we can complete this practice problem. And then again, worksheet 11 has been posted.